Welcome back, everyone. In the part 1 video for section 12.4, we left off talking about z-scores. So a z-score for a data item in a given set tells how many standard deviations above or below the mean that data item falls. And we use this formula to calculate the z-score. Remember, if we're talking about a sample, we use x bar for the mean and s for the standard deviation. And if we're talking about a population, we use mu for the mean and sigma for the standard deviation. So to find a particular item z-score, we take the value for that item minus the mean of the sample or the population divided by the standard deviation for the sample of the population. So it's x minus x bar divided by s, or x minus mu divided by sigma. It's always item minus mean divided by standard deviation. So let's do this for a few examples. So the weight of newborn infants is normally distributed, and the mean weight is 7 pounds. The standard deviation is 0.8 pounds. And we are going to find the z-score for different weight newborns. So let's think about a 9-pound baby. Using our formula above, assuming that this 7 and 0.8 are values for the population, all the newborn babies in a certain time period, the z-score for a 9-pound baby will be the value of the item x, which is 9, minus the mean, which is 7, divided by the standard deviation, which is 0.8. So when we do 9 minus 7, we get 2, divided by 0.8 is 2.5. So a 9-pound baby is 2.5 standard deviations above the mean. So if you remember back to part 1, for section 12.1, that's pretty far away from the mean. Remember, 95% of data lies within 2 standard deviations of the mean. A 7-pound baby, remember that the mean was 7 pounds, so when we compute the z-score for something that's equal to the mean, we get x minus mu, or 7 minus 7, in the numerator there, which is just 0. So it doesn't matter what the standard deviation is. If we're looking for the z-score of something that is the same as the mean, that's just going to be 0. So a 7-pound baby is no standard deviations away from the mean. It is equal to the mean. And then a 6-pound baby, how small is a 6-pound baby? 6 minus 7 gives us -1. Notice that it's negative now, divided by the standard deviation of 0.8 gives us a value of -1.25. So if you are lower than the mean, your z-score is going to be negative. If you're larger than the mean, the z-score is going to be positive. A 9-pound baby is more standard deviations away from the mean than a 6-pound baby is. And that makes sense, right? 6 is closer to 7 than 9 is. Let's do another example. IQ scores are another item that are normally distributed across populations. So let's say the mean for IQ scores is 100 with a standard deviation of 16. And we want to know what IQ score corresponds to a z-score, too close, of -1.5. So first, just theoretically, what does this mean? A z-score of -1.5 means we're 1.5 standard deviations below the mean. So our mean is 100. and we want to know what value x is 1.5 standard deviations below that mean. So we can think about computing with standard deviations, or we can just plug everything into the formula for the z-score. Z is x minus mu divided by sigma. So what we want to know is what x gives a z-score of negative 1.5. So I set up this formula. Negative 1.5 is x minus 100 divided by 16. To solve for x, I multiply both sides of the equation by 16. So the right-hand side becomes x minus 100, and the left-hand side becomes negative 1.5 times 16. So what is 1.5 times 16? 24. Negative 24 is x minus 100. Now I can add 100 to both sides. So on the right hand side I get x, and on the left hand side negative 24 plus 100, or 100 minus 24, is 76. So an IQ score of 76 is 1.5 standard deviations below the mean. The next question, what IQ score corresponds to a z-score of 2.05? This number is interesting because there is a group called Mensa that's like a fraternity for people to join if they have an IQ above 2.05. So remember, 95% of people fall within 2 standard deviations. So this is just above 2 standard deviations. And we did this in the video for 2.1, part 1. If this is our mu, and this is 2 standard deviations above, if 95% of people are within 2 standard deviations, that means 5% is in the tails, which means 2.5% of people are in that upper tail. So Mensa accepts people with, or people, the top 2.5% of people for IQs. So what IQ score do you have to get in to there? We can set this up like we did in the previous example, still using this formula. Z is x minus mu divided by sigma. 2.05 is x minus 100 divided by 16, because we're still working with the same mean and standard deviation. So 2.05 times 16 is 32.8. And then when we add 100 to both sides, we get that x is 132.8. Which Mensa rounds up to 133. So if you have an IQ of 133 or above, you get to be in Mensa. Next, we'll talk about percentiles. So the nth percentile is the data item in a distribution that is n percent, that has n percent of the items in the distribution below it. So for example, if you're in the 95th percentile, that means that your score, your height, your IQ score, whatever, is bigger than 95% of all the other individuals in the population that you're in. So it's closely related to z-scores. Let's think about this example here. For newborn weights again, remember the mean was 7 pounds and the standard deviation is 8 pounds. 7 pounds, which is the mean, would be what percentile? 50% of the data are below and 50% of the data are above, because remember, the mean and the median are the same in a normal distribution when it's symmetric about the mean. So 7 pounds, the mean, is the 50th percentile. So if you're in the 50th percentile, that means half of the population is below you and half of the population is above you. So if you have a baby that's 50th percentile, or say they're perfectly normal, right in the middle, healthy weight. Now let's ask, what percentile is a 7.8 pound baby in? 7.8 is 1 standard deviation above the mean. So 50% of the data is below the mean on this normal curve. 1 standard deviation above gets me to 7.8 pounds. Remember the 68, 95, 99.7 rule. 68% of the data is within 1 standard deviation of the mean. So that means 1 standard deviation above, just this slice here, has 34% of the data in it. So a 7.8 pound baby is bigger than 50 plus 34, or 84% of babies. So a 7.8 pound baby is in the 84th percentile. So 84% of babies are smaller than that baby. That means this baby is in the 84th percentile. Lastly, we're going to talk about confidence intervals. So in a sample of size n, there's a 95% probability that some percent obtained if we conduct a survey in that population. There's a 95% chance that the percent that we get is going to be within 2 standard deviations of the true percent. So let's say I take a sample of 100 people and I ask what percentage of people like chocolate ice cream. I'm going to get some percent. There's a 95% probability that the percent that I get is within 2 standard deviations of the actual percent of people that like chocolate ice cream in the whole entire population. So we're using confidence intervals to make a guess about an entire population from a small sample of that population. So when you see statistics given like 48% of people prefer Joe Biden, or 65% of people say they'll never get on a cruise ship, those numbers, obviously you didn't get asked that question, so they didn't ask everybody in the world that question. They asked a small sample of people and then extrapolated those results to the entire population with a particular degree of confidence. So let's see if we can make that make more sense. Note this nifty formula. 2 standard deviations is approximately 1 divided by the square root of n times 100%, where n is your sample size. So plus or minus this value, 1 divided by the square root of n times 100, is what we call a margin of error. So maybe you've noticed in like political polls or things like that, when you see a statistic given in the news, a margin of error given with it. Let's do an example to see if we can make sense of this. Let's say a survey of 1,000 adults found that 33% of those surveyed exercise daily. We want to find a 95% confidence interval for the true mean of adults that exercise daily. So what are we trying to do? Our population is all the adults. Let's say maybe in the US. So that's millions and millions of people, right? So we're just going to survey 1,000 people randomly, and we talked a little bit in section 12.1 about how to conduct a random sample. So we're going to try to say something about the population from just these 1,000 people. So our margin of error is going to be calculated using that sample size of 1,000. It's going to be plus or minus 1 divided by the square root of 1,000 times 100. And if I work this out in my calculator, I get 3.2%. So what this tells me is whatever value we found, which was 33%, there's a 95% probability that the actual number of U.S. adults that exercises every day is either 3.2% below or 3.2% above what I found in my sample, 33%. So I can write out a confidence interval, the value that I obtained in my study, 33, plus or minus this margin of error, 3.2%. If I subtract 3.2 from 33, I get 29.8. And if I add 3.2 to 33, I get 36.8. So a 95% confidence interval is from 29.8 to 36.8% of United States adults. Just to restate this one more time, the way we would typically say this, the way we should report our results, we are 95% confident that the true mean of U.S. adults that exercise daily is in between 29.8 and 36.8%. That doesn't mean that the true mean is definitely in here. It just means there's a 95% probability that the actual mean is in here. So take statistics that you see in the news with a grain of salt. If you see that, 51% of people preferred Joe Biden or something like that, that doesn't mean he's a shoo-in. You need to know what the sample size was, because that's going to determine what the margin of error is. Notice, the smaller the sample, the larger the margin of error. Let me make that note up here. The smaller the sample, the larger the margin of error. So you may be wondering, well, how can I get better than 95% confident? How can I be 99% confident that I've captured the true mean? It doesn't just have to do with sample sizes. There are ways to find a 99% confidence interval. that don't use this particular approximation. That's a little beyond the scope of this class though. But in case you're wondering, yes, you could have any degree confidence interval that you wanted. 95 is what's often reported in the news though, in like popular statistics. One last comment here. So far we've just talked about normal distributions which are symmetric around the mean. It may be the case that our data is not symmetric. We could have outliers, meaning very large or very small values in our data sets. So if our data is not symmetrical, if our outliers are high, we would say the graph is skew right, and if our outliers are low, we would say the graph is skew left. The median of our data, remember, is the number in the middle, is still going to stay at this peak, the number right in the middle. But outliers pull the mean away. So if your graph is skew right, your mean is going to be pulled to the right, up towards those outliers. And similarly, if your graph is skew left, the mean is going to be pulled to the left. So one interesting example here where things are skew right could be incomes. If there's some very, very rich people, that's going to pull the mean, which is the average income, up. So if we say, and I'm totally just making up a number right here, the average U.S. income is $70,000. That doesn't mean that, like, if you picked a random person off the street, that's what they make, because the average takes into account the outliers. So when you're talking about something that's drastically skewed right or left, the median is going to be a better measure of central tendency. So just something to think about if you're not in a normal distribution. That is all for section 12.4.